All right, excellent. Well, hello everyone. Thank you for coming. So I'm George, as introduced, and this is a joint work with Pascal, Jahrim, and Guido, who are somewhere around here, from the University of St. Gallen in Switzerland. And this presentation about our work on disequality graphs that kind of extend this magical data structure called the E-graph that's kind of very efficiently stores equalities and is able to reason about congruence. So E-graphs are these fundamental data structures that you will inevitably see inside provers or solvers. And essentially, they comprise of two operations. So the first one is adding equalities. For example, f of a GB is equal to c. And you can also find the equivalence class of terms. So for example, if I query for the equivalence class of c, I will get the equivalence class of f of a GB. And this is how I can tell that two things are equal. Right, so an E-graph is a graph. And so it has vertices and edges. And there are two kinds of vertices. The first one are E-classes, supposed to represent equivalence classes. I represent them with a circular here. And we can add things inside them. So here I add A, which is called an E-node, a term, an atom, inside of this equivalence class. This is yet another equivalence class that contains the atom B. So I can add things like that to my E-graph. So this is the application of f of A added to the E-graph. Except this is not actually how we do it, because we know about A. So the E-graph knows about A, so instead it just represents it like this. So this edge, if you think a little bit about it, this is the thing that guarantees congruence. So this term now represents f of A and anything which is equal to A, f of anything which is equal to A. So to make this example a little bit more interesting, let me just add f of B as well. And this is how then we would equate two things inside of an E-graph, because now I just added things. If I want to say that A is equal to B, I just kind of merge their E-classes together. I fix the arrows, and I'm not actually done. Because if I scrutinize a little bit, these highlighted nodes, they represent exactly the same thing. They both represent f of A and f of B, so they ought to be equal. So their E-classes ought to be the same. So now I have to read their equivalence classes. And I end up with this E-graph. So this example, I will go back to it multiple times in my presentation later on. So now that we are all experts on E-graph, I want to present to you my first contribution, which is a formal framework to reason about E-graphs. And the objectives of this framework is to be abstract and extensible. So abstract in the sense that it ought to kind of cover as many implementations as we are aware of, and extensible so that we can define extensions, which I will talk about a little later in the talk, so that kind of proving correctness theorems, proving bounds on these things is easy. And the other contribution which we did is that we present a novel correctness algorithm for these E-graphs that isn't just one giant proof, but we rather refer to a lattice. I will come to this in a little moment. So if you, in the next few slides, there will be definitions, theorems. You don't have to read them. I will guide you through them. If you don't like to see the stuff, you can go on your socials, tweet about the talk, and you can come back in a few minutes. So the way we define, for example, an E-graph is it's a triple of classes and nodes. One of the choices we did is that, for example, classes don't need to be different than nodes. This would cover some implementations that don't actually talk about classes, but rather use some canonical E-node to represent the class. Another kind of feature we have is in this complicated rule, which talks about how to merge two things, which kind of is this thing here when we want to equate two classes. But this is the thing I want to focus on, and here we are constructing the reflexive symmetric transitive closure. A lot of implementations kind of reduce this to using a union-find data structure, which essentially does this. So this would justify why these implementations are correct. And the last feature I want to show you is, again, how we did this correctness proof. What we did is that we kind of showed that the E-graph is correct, that it generates the smallest reflexive, symmetric, transitive, and congruent closure of some set of equalities by essentially referring to the lattice of equivalences. In 3.14, in theorem 3.14, we show that the smallest one in the lattice implies the relation that you get from the E-graph. In 3.15, we show the opposite, and they are equal as a corollary. This was pretty helpful for us because when we did the extensions later on, all the effort had to go on theorem 3.15. So we had a much kind of stronger theorem to work with, which made things easier. Okay, those on the socials, you can come back. Now I want to tell you a bit about disequalities. I think they don't get the appreciation they should get, and they are not covered often. And I don't have a slide for this, but if we go back to the first presentation in this session had a lot of disequalities in it as a motivation, but actual motivations also include SMT solvers. So here I have this formula, n is equal to m, and ffn is not equal to ffm. And I want to give it to an SMT solver to find assignments for n, m, and f if they exist. So how does this happen? The SMT solver converts it to a Boolean formula, p and not q, and it stores the aliasing that p is an equality between n and m, q is an equality between ffn and ffm. It queries the SAT solver for a model. In this case, yes, it's satisfiable. This is the model. And it feeds it into the E-graph. And now the E-graph has to use the knowledge that this equality is false to somehow figure out that there is a contradiction. So it has to be able to reason about disequalities. The other motivation comes from our project. It's called POPL'. It's an automated inductive theorem prover. We presented it at PLDI last year. And POPL' has a lot of properties. One of them is reasoning about disequalities. And when we wanted to explore the effect of reasoning about disequalities on the quality of proofs, what we did is we did a little experiment. We took the theorem that addition is commutative. We took two versions of POPL', one where disequality is enabled, one where it's disabled, and we tried to prove the theorem this way. What we got is essentially this thing. So this thing is a graph of all the states that the prover was in and all of the transitions it went into. At the surface, this looks like disequalities are horrible. They go kind of all over the place. There's a lot of things to go. But the caveat is that they both ran in the same amount of time. So kind of disequalities helped pruning a lot of these branches, and we went to discover many more states that we wouldn't if we didn't have disequalities. And with that, hopefully, I convinced you disequalities are useful. And now I want to show you 3 ways how to do that inside of E-graphs. The first one is actually 2 versions inside of the paper, and they fall under the umbrella of what I call valued embeddings. And in here, the observation is that equality is a binary Boolean function, right? And an E-graph is meant to represent functions, so why don't we let the E-graph know about this function? I'll go back to my example from the beginning, and I'll show you how this works from here. So if I want to say that A is equal to B, I will not merge as before. Instead, I will just add these 2 terms, saying that the equality of the respective classes is true. If I want to say they are false, FFA and FFB are false, I would do the same, except I equate it with false. Now what I would do is I would need to also reflect the axioms of equality inside of this graph. For example, symmetry. I would need to duplicate every equality and kind of switch things around. I don't do this in the presentation. It just makes this very complicated. So trust me that there's this stage at this point. But now how do we find out that there is a contradiction? What we would do is then first we would look at this pair. We know that this equality is true, so the graph ought to reflect this by merging the 2 E-classes. So now what it knows is also true inside. But we're not done, because after doing this, we look at this equality. This equality says that the same equivalence class is equal to itself. And of course, by reflexivity, this has to be true, which means the 2 classes at the bottom have to be merged together. And after doing that, this is the graph we get. If we focus on this part, this means true is equal to false. And so this is how we would find if there's a contradiction. The second approach is I call unvalued embedding. And here we are still embedding, except we're not giving values, because the main observation is that this equality is just a proposition, and the mere existence of some of these terms is a witness for the disequality. I'll elaborate a bit more. So going back to the same example, now when I want to say that FFA is not equal to FFB, I just add this term. in the valued embedding earlier, I assigned this a value. I said whether this is true or false. Now I just add it like this. If I want to say that A is equal to B, now I just do as classically is done in eGraph, and you merge the two equivalence classes. And the contradiction can be found by kind of looking at this pattern. This pattern is saying that an equivalence class is not equal to itself, obviously a contradiction. And the third approach is structural, and in many ways, the third approach is the first one historically. So this is a quote from Nelson in his PhD thesis from 1980, and this is the PhD thesis that introduced eGraphs. He writes, given a disequality, we must add structure to the graph so that if the nodes ever become equivalent, the program will detect it. The obvious way to do this is to store with the root of each equivalence class a circular list of nodes that are forbidden to join the class. Elaborating a bit more on it, go back to my example. If I want to say that FFA is not equal to FFB, now all I need to do is add this edge. This dashed edge between E classes represents the fact that they should not merge, or that they should not be equal. Now when I equate A and B to create a contradiction, this becomes a self-loop. And in fact, it is this pattern, this self-loop, which is the indicator that there is a contradiction. Okay, so I've shown you these three approaches, 4 in the paper. Why did I do this when the last one was like 45 years old now, published and all of that? It's because when we looked in applications to see what is actually used inside of SMT solvers, and we looked at these SMT solvers, we did not find the published technique, which is the Nelson one, except in OpenSMT2. So OpenSMT2's eGraph is exactly as Nelson describes in his PhD thesis. Z3, on the other hand, embeds both disequality and equality, but without giving them a value. So this is why it's a little bit off from the unvalued, because it also embeds equality. CVC5 also embeds both, except it gives them a value, but without needing to reflect all of the axioms, and kind of refers back to the unvalued embeddings way of finding a contradiction. So what gives? Which is better? And so this is kind of what we wanted to do. So the first thing we did was we used our nice extensible framework, which I talked about a bit earlier. We extended it to talk about the 4 variants. And we proved they're correct, and we proved some bounds on them. I will not show you the theorems about the bounds, because the results are kind of the same as the case studies. So we have some case studies, and it's exactly the same. So I will only show you that. So the first case study we did is that we took our inductive theorem prover, POPL', and we made it use these 4 eGraphs, and we kind of measured the resources it took. So the first resource is time, and this graph, what you see is on the x-axis, the time, and on the y-axis is how many benchmarks it could solve given some time. So what you should be on the lookout for are very steep, kind of fast-growing lines, because these are the lines corresponding to the approach that is better. And in this case, the structural one, so the one with disequality edges, performed better time-wise than the unvalued embedding than the valued embedding. And we didn't only measure time, we also measured memory, but by proxy of counting the numbers of classes and nodes inside of the eGraph. And what we saw is exactly the same for the application of inductive theorem provers. The next case study we did is that we implemented the core of an SMT solver, which is, or a kind of part of the SMT solver, which is the equality and uninterpreted function part of the SMT solver. And it uses internally a mini-SAT and an implementation of the eGraph with the 4 approaches to reason about this equality. Then we used the standard SMT-lib benchmark, which contains about 7,600 files, and we did the same experiment as before. So we ran it against time. We ran it to see how much time it takes for each approach. And what's obviously clear here is the very wide gap between the valued embedding and the unvalued embedding. And this really shows the kind of how expensive it is to reflect all of these axioms inside of the E-graph. Again, we did this also for memory by counting the classes and the nodes, and we got the same. So, in summary, invite you to read our paper. We have inside it an abstract and extensible E-graph framework, and the 3 approaches for handling disequalities, an evaluation to compare these things, and one more evaluation that I didn't get to show you. So with that, I thank you. I invite you to read the paper, and I'm open for questions.
Hi, thank you for the talk. I was wondering whether you knew why the valued embeddings were so much slower. Like maybe if you had a better data structure like union find, you wouldn't have to store as many things in the relation.
So you're asking about why this gap is so big?
Yes.
Yeah. So I will try to go back to just about here. So I kind of added these 2 things, right? So I would first of all have to duplicate them to do symmetry. Sometimes I would also need to add versions to handle reflexivity. I would need to reflect all of these things. I need to iterate on them because I might make progress, as in here. And while I make progress, I need to add maybe additional equalities. And so this step is iterative. It's not like a 2-way process. So every time you add things, you have to check whether you can prove more things out of it.
All right, thank you.
Hi, thanks for the talk. Similarly, any intuitions on why Nelson wins?
I think so. So if you squint really hard here, what you will see is that these 2 edges, or rather the role that this node is doing, it's just to connect these 2. It's just a way to connect these 2, but through an E node which is useless and also has a useless E class attached to it. If I show you kind of this way, so this is a much direct way. In memory, this edge would just be a pointer somewhere inside of the E class, whereas here you would have to add this E class inside of the hash cons, inside of the list, and then also record the E class. So there's much more stuff to record.
All right, the disequality itself is not kept anywhere as an atom in the structure. The disequality itself is not kept as a term in the structure anymore.
No, exactly. Okay. So for the sake of the stream, I will repeat the question and let me know if that's correct. So you asked if the benchmark I did, probably for the SMT lib, or so if they reflect realistic data. So I did. If the question is whether I kind of run the same benchmark through, let's say, Z3, CVC5, and OpenSMT2, we did not do that because there's so many factors other than the treatment of this equality inside of the solver, which is why we kind of ended up writing our own. Ideally, and this is left as an exercise or for some PhD student or master student, is try to extract actually the implementation of the E-graph that they use and really benchmark just the implementation. This would be the next thing to do there.
Great talk, Tom Ball, Microsoft Research. So did you look at instruction cache versus data cache? Because I imagine layout of data structures plays an important role. That's been my experience from watching Leo Demora create like 10 different SAT solvers, and all the packing, it matters.
Yeah. So this is my intuition. My intuition is that, again, because I'm using this, what is it? This pointer here as opposed to this additional indirection, I think is kind of maybe more cache friendly. I did not look at it. This is purely speculation.
So